Hi everyone, my name is Parmar Tanvi and I am a part of Team VRT Avionics. Our rocket name is Nova. Me and my teammates Dhruval made a cansat named ARK-1. In this video, I will walk you through the PCB design I worked on for our avionics system. I will be showing the complete process from the schematic to the final layout of our PCB while explaining the important decisions along the way. The aim is to make this design clear and reusable for anyone on the team in the future. Let's get started to the introduction of CANSAT. CANSAT, the name suggests it is the combination of soda can and a satellite. A CANSAT is a miniature satellite shaped project fitting into the volume of 350 ml soft drink can that serves as a simulation of a full scale satellite for educational purpose typically launched by rocket. Here you can see some images of CANSAT so that you can visualize it. Now I move forward to the sensors which we used in CANSAT. The first sensor is SHD31DIS. It's a temperature sensor. It measures temperature and humidity. Next sensor is BMP390. It's a pressure sensor which measures pressure and temperature. The third sensor is MAX M10S00B navigation sensor. It provides robust and accurate positioning data needed for navigation, flight path monitoring, and landing location. BMA 400 accelerometer. It can be used to track the CANSAT's G-force during launch and descent, measure the rotational moments, and monitor stability during the flight and landing. VEML6075, it's a UV sensor, directly measures intensity of UVA and UVB radiation in the atmosphere at different altitudes. RF module, the microcontroller sends the data packet to the E3290 T30D module through a TTL serial port. The module then uses LoRa to transmit the data wirelessly to the ground station. Then we used LIS2 MDLTR magnetometer. With the combined data, you can implement a tilt compensated electronic compass algorithm on your microcontroller to calculate the CANSAT's reading relative to magnetic north. Then we used Geiger Counter. It's primarily used for detecting and measuring ionizing radiation such as alpha particles, beta particles, and gamma rays. We used a ESP32S3 microcontroller, which is a brain of our CANSAT. Now we move towards the schematic, but first of all, we have to find out the microcontroller and the sensor which we used for it. So first of all, we go into the LCS electronic website for it, and we used ESP32S3 room and for R2 microcontroller. So we search on it ESP32S3 room 1 and for R2. This is it. And we will see here it is. So we copy this LCSC part. And now for the schematic and PCB designing, we use open source platform EasyEDA for it. There's an online and standard edition. We give his name is file, new and open project, new standard project, and we give name is cansat. We also give the description of it. If you require, you can give the description also. Now this schematic design is open. So it goes into the place and symbol. And here we place the paste of it. ESP32S3 room 1 and for R2. This is the schematic diagram of it. This is PCB and this is the actual model. So we will use it here and that. Now we place and symbol this sensor which we used. So we will name SHT31 VIS. It's a temperature sensor. So we will go to that and yeah, we will find out this is temperature sensor. Then we go to another and symbol, change it BMP 390, which is our pressure sensor. And place over here. Then we will use PMA 400, it's accelerometer. Place it over here. And we will use navigation sensor, MAX M10S00B. It's our navigation sensor. Place it over here. Go to the place, symbol. And next sensor is VEML 6075. It's our UV sensor. Place it in here. Look at this is our UV sensor. Then our magnetometer and sensor is magnetometer. Place symbol LISB 2MBLP. Okay, this is the sensor. We copy this LCSC part and paste it over here. Yeah, we can find out this is our magnetometer. Then it is custom recipe. So in this, we use the module of a microcontroller. So we required USB port, we required boot button, we required reset button for it. So all the this thing which is already in the development board, but we don't use development board, so we will include it. So first we go to the LCSC and search USB-C type port for that. Yeah, very good. For this, our USB port. Right. So we again copy this, paste it over here, symbol, yeah, we paste it over here. For this USB-C type, we place it over here. Great. Then we go to the place and symbol. We use button for it. So first of all, we have to find out the switch, equal switch in LCSC. So we required a push button and a enable button. So we use only push button we required. This is the push button LCSC card C221869. We go to it. Yeah, we will get place it This is for boot. This is for enable. And yeah, then we also need screw terminals. The screw terminals were required at DB 125 dash 3.81 2P when screw terminal were required for it. This is yeah. So we will place it over here. Green. One is for power. Another three is used for pyro. Then we will also need a voltage regulator. So voltage regulator name is TLV 76733RBT. This is the voltage regulator. Yes, we place it over here. Then also the required LED for the indicator. We have to select which LED we can use. We have to also know about the footprint of it. We can use it. So here we use the LED just for the indication of that. Then we also required an antenna. So its name, we go to the LCC U.FL R SMT 110. This is on that we mount the antenna. So we required it. This is copy it and paste it into the EasyEDA. Click this over here. And we have another sensor. It's Geiger Counter. But in this, there are only three pin. So we use terminals for that. We use library, common library we will use. Scroll it down. And yeah, it's third pin. So we will use it. We also required RF model. So we start the S32 900 T30D. It's a RF model. So we can place it. Yes, we can place it here. Then we also required MOSFET. So this is our MOSFET. Name is BO3400A. Okay, so we will place it. We require two MOSFET for the ejection. And this MOSFETs are work as a switch. Then all the components are placed here. We also need some resistor and capacitor for the connection. And we all know this is the ESP32. This is work as a master, and all other sensors are working as a slave. So we connect this whole sensor to the microcontroller pin, which pin it is defined in ESP32 datasheet. So connection is started. First, we connected to the UV sensor. We require here this is 4 pin and ESP32 having many pins. You can see here ground with 3v3 enable pin and etc. So we just find out in datasheet that which pin is working as which. So first in datasheet this is provided which pin is working as which. So first this is ground, this is 3v3, this is enable. This is enable is connected to the reset button. So this is working as an enable pin. Then all other pin are there and UV sensor having ground and VDD. So VDD is connected to the 3v3, ground is connected to the ground, and SDAT, this pin is connected to the SCA of microcontroller and SCL to the microcontroller. And we know that in this pin, we can say that this is working as I2C protocol. So in ESP32 having I036 and 37 pin is working as I2C protocol. So we label it. So first we have to wire its wire and we can say it's by W connected here, then connected here. Then we use net label. This SDA and this IO36 is SDA and I37 is SCL. So we just name as SCL. So this two pin is working as SCL and SDA. Now we move towards to the UV sensor. So we move towards the UV sensor. Then we place W for the wire and we find out this. Then it is ground. This is 3v3. When we use this 5 volt or 3v3, we just change the name of it. It's plus 3v3. And here we use ground. This is ground. Now we connected SCL pin. So we just place, we don't connect it to this microcontroller. So because it is too messy and we cannot see the proper connection. So we will use net label for it. So this net label, we just copy it and paste it over here. Similarly, SDA, we will copy it and paste it over here. So this connection is over of UV sensor. Similarly, we can connect all the sensor and we also required resistor and capacitor as a pull up and pull down. So now we all the connected sensor. So as I said earlier, that we required some resistor and capacitor, then you can find out easily the connection of that. So here we can see that this is the power terminal, which is this, and we have a power terminal one pin is connected the 5 volt and second pin is ground, and this is our voltage regulator. As we can supply is 5 volt, and this voltage regulator is converted into the 3.3 volt. So indication for the indication purpose, we used LED for it. So as we can find out that the power is converted into 5 volt to the 3.3 volt, and this is the capacitor which is required. Then we have a boot button and reset button. So similarly, so this boot button is connected to the ground and with 3v3 pin as 10K and 0.1 microfarad capacitor and resistor, and which is connected to the boot label, and this boot label is connected to the flat computer of IO0. So this is, and similarly for reset button, this is connected to the enable of microcontroller. This is named as enable. Then we have a Geiger counter terminals. As I said earlier, that Geiger counter having three terminals. First is connected to the ground. First is 3v3, second is ground, and third is connected to the SIG, which is connected to the microcontroller IO 5 pin and with 72 ohm resistor and zero point 0.1 microfarad capacitor with 3v3. Then we have accelerometer BMF 400, which is connected VDD IO, which connected to the 3v3, and all pin which is not required, we just put it as cross. Then we have connected CSV pin to the 3v3, and this is SDX and SCX, which is defined as it is working as I2C protocol. So SDX is connected to the SDA and SCX is connected with SCL with capacitors. Then we have temperature sensor. This is temperature sensor. Similarly, I can say the temperature is working as I2C protocol. So SDA is connected to the SDA pin and SCL is connected to the SCL pin. ADDR pin is connected to the ground, and VC, VSS is also ground, and VDD is connected to the 3v3 with 100 nanofarad capacitor. Then we have a pressure sensor. This is BMP319 as suggest. This is SCK and SDI. So we can say that this pressure is working, sensor is working as I2C protocol. So we use SCL and SDA pin. This is also in microcontrollers. So this is known, we can communicate this sensor and microcontroller to the I2C protocol. So SCL is connected to the SCK and SDA is connected to the SDI. VSS is connected to the ground, and VSS is also connected to the ground. VDD is connected to the 3v3 pin. Then we have USB-C port. As you can see here, there are many pins are there. Ground is connected to ground. Here we can say V bus. This is V bus, which is connected to the V bus with a diode for the protection purpose. And there are many V bus. Here so you can say four V bus is there. So we just label as V bus as first, and then for three, then we just label it V bus. So this is working as uh, this similarly. So we cannot add four diodes for it. Then DP2 and DP1, these two pins are same. So which is connected to the diode and with 22 ohm resistor with USB-T plus. This is also known as differential pair, and this is the connection of USB protocol. The inbuilt there are USB protocol of ESP32S3 room. So this is the pin of IO20, which is connected to the USB-D plus, and IO19 is connected to the USB-D minus, same as DN2 and DN1, which is connected to the diode and 22 ohm resistor with USB-D minus. Then we have a magnetometer. So magnetometer is also working on I2C protocols. So SCL is connected to SCL, SDA is connected to SDA, ground CS is connected to the ground, and ground is also connected to the ground. Then VDD IO pin, which is connected to the 3v3 with some capacitor value and ground. Then we have a UV sensor, as I show you to the UV sensor connection. So first we just add the connection. So 3v3 is connected to the VDD, SCL is connected to the SCLK, and SDA is connected to the SDAT, and ground is connected to the ground. We just add this register for the purpose that we cannot damage our UV sensor, so that. Then we have RF module having many pins, M0, M1, which is M0, M1. AUX pin is connected to the microcontroller pin. AUX is I04, and VCC is connected to the 3v3. RF module having two pins, RXT and TXT, which is RXT and TXT, which is UART protocol. In ESP32 having also UART protocol, which is this. TXD0 and RXD0, which is working on UART protocol. So this two pins is connected to this, and this is 3v3 volt. Then we have a navigation sensor. This is as through I2C and UART protocol. Both are working. So we use UART and I2C for that. So SCN and ST is connected to this, GPRX and GPRTX. It is connected to microcontroller RXD and TXD pins as shown earlier. And then VDD is connected to the VDD, which is also 3v3 pin. Then ground is also connected to the ground. And we also need a external antenna for that. So we use VCC RF to the inductor 27 nanohenry, which is connected to the signal of antenna, and both are pin, another both pin is ground with and 27 Henry, nanohenry, which is connected to the 10 ohm and zero point 0.1 microfarad with 3v3. And this is for the pyro. For the ejection purpose, we used three terminals. So this is the power screw terminals is there. So first is for pyro 5 volt as is given to the 5 volt. Then second is ground. Then we have a MOSFET to trigger it out. So this is working as a switch. So when this is pyro 2 and pyro 1, which is connected to the microcontroller pin of IO. Yes, this is IO 47 and 48. So this is connected to that and 220 ohm resistor with 10 k ohm resistor to the MOSFET. Then we have testing terminals of it. Just for the testing purpose, we use testing terminals SCL, SDA, and ground. This is 3.5 pitch with three terminal testing terminal is there. So we just completed our cansat schematic. Now we move towards to the PCB designing. So just we place design and convert schematic to the PCB. If you take nets, it's very good. As I said earlier, you just have to connect cross. This is this cross to the pin which have you not used. So now this is the PCB design. Then you have to uh, give the size of that. So we have a board outline as a rectangular. So we have a round rectangular shape of that. And radius is we have to define that which radius I have to go on. This I is 4 and according to your dimension or according to your requirement, you can change the width and height of that. So I just place it at width is 50 and height is 80 and apply. So yeah, this is my PCB outline. This purple line is my PCB outline, and this is the components which I place here. So first thing you have to keep in mind that when you have to create your PCB, the first thing you have to place the components in such a way that you cannot mesh up the connection, and you just keep the connection near about so that you just not place the routing too far to the components and big deal of that. So we just place our connection. So we just place first our ESP32 like here. Yeah. When this is RF model, so this is we just place it in bottom. So in PCB there are many types of layer, so you can place according to that. So we used four layer PCB for this. So the top layer, this is bottom layer, and we just place in bottom layer. So we just place into the control B. So this is in bottom layer. Then USB port. This USB port is a connection is very simple. You just have to mind it, keep in mind some points. Yes, this USB port is connected to this like this. Then opposite to the your microcontroller, you can just place it this. Then similarly, uh, the connection of boot and enable pin is same. We mostly use this switch and enable pin near to the USB. So we just placed enable pin to here, enable button, and the switch button here, right? And this antenna is in this RF module is in bottom layer. So we just move that. So now this is the power terminal where we just placed it here. Then many other sensors are there. It's you can define. Then it is opposite to the USB port, and boot button and enable button is near about the USB. And this, if more components are there, so you can place it on the bottom side also. Then the screw terminals is near about the outline, so that you can uh, uh so that you can give it the wires to it. Then the sensor is connected to the near about the connection, as you can see, and the connection of a control connection of this sensor. So in connections of that, we have many resistor and capacitor. The capacitors are there to connect it with the sensor. So we have to keep in mind that this connectors of connected of sensors and the sensor, resistor, and capacitor, which are in one sensor. So this one sensor having many resistor, as you can see here. This is the sensor. So L2, which is there. So we have to place it near about, so that the connection is so easy. Then this capacitor is also the part of this sensor. So we place it in near about, so that this tracing is so easy for us. Then diode, which I used for the USB. So I place it near to the USB, so that connection is too easy for me. Similarly, you can do connection near about, like this sensor is this sensor. This is the sensor. This is the power terminal. This too is our pyro. This is and this is our sensor. This is this is our antenna, and this is our testing terminals. This is our power terminals. This is also a sensor. All other are capacitor and resistor, which is connected for the safety of the purposes. So this connection is not for messy. So we just have to place it this connection near about the sensor, so that it is not for trouble our this testing terminals here. I just place it. So it's also okay. So this is our antenna. So we just put this is our antenna, and this is our navigation sensor. So we just put this antenna near about the navigation sensor, so that the routing is easy for us. Then this is our another sensor. This is our pasting terminals, which we can put here. This is our Geiger counter. terminals. So we can just put these terminals are basically we put in this place of outline so that it's not hidden for us. Then this is the temperature sensor. We near about putting the sensor adds according to the connection of it. As you can see here, the connection is less than this. So we just put it down. So the connection is kind of clear to this. Right? We can just connect all the things to that. Now all other is just a capacitor and resistor. So you can put it according to that. So this is all. All other are just LED and sense resistor and capacitor. So which is connected by your side. So now we move forward to the Pro Edition just for the better features of PCB designing. So we go to the Pro Edition of EasyEDA and migrate. This is our cansat. So we just place confirm. So our schematic and what we done in our standard edition. Just it is import in Pro Edition. We just rename as help one in new window. We just for so now I just put copper region first. So where we I found the copper region. This copper region is used for the purpose of power. So that's why in USB, if we use USB, so we must use copper region as a polygon on a shape. And this is this quite good. This region is made up by the copper. And as we name suggests, you can give any name. 5 volt I give. So this is copper region. You can see this has become copper region. Now I'm not do that. So now um, we move forward to the routing. So I just give you the brief of how to do routing. So I just place Alt W. So it can be net length as this and just get. Now you can see here this ground is in this power terminal is in top layer and this LoRa module ground is in bottom layer. So we just have to place double tap and this is now in a ground. This is now in a bottom layer. So we just place in ground. Similarly, there are many types of routing. There are mostly we just have to keep in mind that our three type of routing. This is the grid size is same as it's not different. It is 2.54, sorry, 2.54 mm. This is great. Then we just go to into route and there are, you can see single routing. You just place Alt W or single routing. Then you have differential pair routing. So this is the concept of differential pair routing. It's a pair routing is very different from others or multiple routing are there. Equal length tuning routing, it's required when the differential pair routing it's not match as a DRS. This is also differential pair equal length routing. Then auto routing, it's option, but we just prefer not auto routing. We just prefer we use the routing how to make a router. So this is the mode, and then this is the design. So in the design we can differential pair manager is there, equal length group manager is there. Then check time DRC is there, design rules is also there. And if any changes are needed, we can update the PCB also. Then layout. In layout, we can say this rotate or left in this. Then tools. In tools, we can say layer manager. As I said, our PCB is a 4 layer. So I just name as a copper layer 4, inner one and outer one. So I just place that is a plane zone, and this is also a plane zone. Name is ground, GND, and this is also GND. So basically GND1 and GND2. So we just place name as GND1. Okay. So apply and confirm. Apply successfully. So now you can say this is our top layer. We have 4 layer. So first is top layer, then second is bottom layer, and in between two there are 15 and 16 is an inner side which is ground layer. So if you can visualize, first layer is top layer which is signal layer or a power layer. Then uh, in a bottom side it is a bottom layer, and in between two there are 2 layers which is ground layer. So this is 4 layers we can make. So this is we already make, this is the 4 layer. Then I just told you how to routing. Here we can see this is line is 45 degree. We cannot routing as a 90 degree, so which is not preferable, and we generally prefer line as 45 degree of routing. Then we go to the tools. So we go to the routing and we use differential pair routing, or we can say Alt D you can put also. This is the differential pair routing. As I just scroll down. Yeah. So I just place it here. Now you can see here the name of router. So as we go to the route, differential pair routing. This is not. Yeah. Now we move forward to the differential pair routing. So first of all, we just places the components near about that. So I just put the cards over here. As differential pair routing, we just do it differential pair routing of a USB port of USB D plus and USB D minus and the GPS RX TX pins. So we just do the differential pair routing of this pins only. We don't need all of that in differential pair routing. Then we just place this register over here and this register over here. I just place components in a way that we can connect the things. Then I placed Alt W and I place it Alt W, Alt W over here, over here. Then we have to use differential pair routing. So we just place in route and differential pair routing, or we can place Alt W, also, Alt D. So just place Alt D. As you can see here, the match the rule. It is a green line. We can say it's our good for differential routing. If it is go to the red line, it is not in our rule. So we have to come into the rule and we have to place our routing like that. This is going to good, but if it is in this, we just place this is in a red line. So we just put, and this is solved by go to the route and differential pair equal length routing. So I just, or we can say place or shift A also, and I just place some point over here and just this. This is here. There you can see here as I match the rule. You can see here, this is the green line and I just place. So this is the way the differential routing is there. This is the differential routing of our USB D plus and USB D minus. You have to do the differential routing of GPS, RX pin and TX pins of this. And I just do the components of another components. So you just give an idea of how to do routing and how to do this. So I just place, this is the ground. So I just do Alt W. I just place and this is ground, but this is in a ground. This ground is in bottom layer. So I just do it and this bottom layer. And this is also a ground, but this is in a top layer. So I just go to this and this is in a top layer. This is V bus. So this V bus is connected to, so you can find out this is the differential pair routing of this. And as our PCB is a four layer, so you just have to post down this. This is the enable pin. So this is connected to this. So I just press Alt W. This is our enable pin. This is going like this. And I just down, top down, and here I am just in a top plate. So this is our enable pin routing of enable pin to enable button to the enable of ESP32. So now you can do this PCB. So now you can see here, this is our complete PCB. which is designed at dimension of 80 by 50. This is our pyro terminal. This is our testing terminals. This is USB boot button, enable button. This is our power terminals, and this is look quite so pretty. This is our magnetometer. This is our pressure sensor. This is our accelerometer. All the sensors are there. This is our ESP32. So this is our complete PCB. This is top layer. This is our down bottom layer. And inner two side is this is ground and this is ground one. You can see. So I move forward to the top layer. And now you can see here, this is all the connection of ground. It is connected to the ground, but if you are not connected to via routing, so you use some of the connection via, so you can just place Alt V and this type of connection is there. Then you just select the components are there and just you have to select ground and 3v3, so you can do via this is the via of 5 volt, and you can also similarly do for the ground also by via. So this is our complete PCB. This is our 3D of model this of ESP32. You can see all the component size and width you can imagine. So this is our 3D model, and this is our pressure sensor, and all other sensor are there, temperature sensor, magnetometer also. This is all the sensors are there. This is testing terminals and all the sensors. This is LoRa module. This is ARK-1. So yeah, this is our 3D view of our PCB. So this is our manufacturing PCB. As you can see here, GLC PCB is manufactured it, and this is our PCB ARK-1. So now I complete the tutorial of our PCB. So this is the PCB of our cansat. So this is made by us, and I hope you will enjoy this. Thank you so much for watching this.